The birth of quantum theory marks one of the most important turning points in the history of science, because it represents the moment when humanity realized that nature does not always behave according to everyday intuition. For centuries, physics had been guided by ideas that worked extremely well for large objects: planets, falling stones, flowing water, and moving machines. These ideas reached their most complete form in classical physics, especially through the work of Isaac Newton and later scientists. By the end of the 19th century, many physicists believed that the fundamental laws of nature were almost fully discovered. The universe seemed like a perfectly predictable machine, governed by continuous motion and smooth changes in energy. Yet, hidden beneath this confidence were cracks that would soon grow into a scientific revolution. One of the biggest challenges came from the study of heat and light. When objects are heated, they emit radiation, and this radiation changes color as the temperature rises. For example, a piece of iron glows red, then yellow, and eventually white as it becomes hotter. Scientists wanted to understand this behavior in precise mathematical terms. This led to the study of what is called blackbody radiation. A blackbody is an ideal object that absorbs all incoming radiation and emits energy in a way that depends only on its temperature. Physicists could measure this radiation very accurately, and the experimental data were clear. However, when classical physics was used to explain these results, it failed badly. According to classical theories, especially those based on electromagnetism, a hot object should emit radiation at all possible wavelengths, with energy increasing continuously. When scientists applied these ideas mathematically, they predicted that at short wavelengths, the energy output should become infinitely large. This result was obviously impossible and did not match experiments. This problem became known as the ultraviolet catastrophe. It showed that classical physics, which worked so well in other areas, was completely inadequate for describing radiation at very small scales. At this critical moment, Max Planck entered the story. Planck was a German physicist who was deeply committed to the laws of thermodynamics and classical reasoning. He was not trying to overthrow physics or start a revolution. In fact, he considered himself a conservative thinker. His goal was simply to find a formula that matched the experimental data for blackbody radiation. After years of struggle, Planck made a desperate and radical assumption that would change science forever. Planck proposed that energy is not emitted or absorbed continuously, but rather in discrete packets. These packets of energy were proportional to the frequency of the radiation, and the proportionality constant later became known as Planck's constant. This idea meant that energy, at the microscopic level, comes in tiny, indivisible chunks instead of flowing smoothly. Planck did not initially believe that these energy quanta were physically real. He saw them as a mathematical trick, a way to make the equations work. However, the success of his formula could not be denied. It matched experimental results perfectly, solving the blackbody radiation problem completely. This single assumption shattered the foundation of classical physics. If energy could only be exchanged in discrete amounts, then the smooth, continuous picture of nature was no longer valid at the atomic scale. Although Planck himself was uneasy about the deeper meaning of his idea, other scientists quickly recognized its importance. What began as a technical solution soon became the starting point of a new way of thinking about the universe. The significance of Planck's idea lies not only in solving a specific problem, but in what it revealed about nature itself. It suggested that at very small scales, the universe operates according to rules that are fundamentally different from those governing everyday experiences. This was a shocking realization. For the first time, physicists were forced to accept that their most trusted theories had limits. Classical physics was not wrong, but it was incomplete. Planck's constant, though extremely small, became one of the most important numbers in physics. It sets the scale at which quantum effects become noticeable. In everyday life, this constant is so tiny that quantum behavior averages out, making the world appear smooth and continuous. However, at the scale of atoms and subatomic particles, Planck's constant becomes dominant, revealing the grainy structure of energy and matter. The birth of quantum theory also changed the role of theory and experiment in science. Before Planck, experiments were usually interpreted within existing theoretical frameworks. When results did not fit, scientists often assumed experimental error. The blackbody radiation problem forced physicists to do the opposite, to change the theory to match reliable experimental data. This shift emphasized that nature, not human intuition, is the ultimate judge of scientific truth. Planck's work also introduced a new philosophical challenge. If energy is quantized, what does that say about the nature of reality? Is the universe fundamentally discrete rather than continuous? These questions went far beyond physics and touched on deep issues about how we understand existence itself. Although Planck did not explore these philosophical implications in detail, his discovery opened the door for others to do so. Another important aspect of this first keynote is how unexpectedly the quantum revolution began. It did not start with a dramatic announcement or a bold philosophical claim. Instead, it began quietly, through a technical paper aimed at solving a practical problem. This shows that scientific revolutions often arise not from grand intentions, but from careful attention to experimental facts and a willingness to consider unconventional ideas when old methods fail. The impact of Planck's idea soon extended beyond radiation. It provided the foundation for later breakthroughs, including Einstein's explanation of the photoelectric effect, which showed that light itself behaves as if it consists of particles. This further strengthened the case for quantization and made it clear that Planck's assumption was not merely a mathematical trick. It described something real about the physical world. The birth of quantum theory also revealed the importance of humility in science. Even the most successful theories can have limits. The confidence of 19th-century physics gave way to a new understanding that nature can surprise us in profound ways. This lesson remains relevant today, reminding scientists that progress often comes from questioning deeply held assumptions. In summary, the birth of quantum theory began with a simple yet revolutionary idea introduced by Max Planck. Faced with a problem that classical physics could not solve, Planck proposed that energy is exchanged in discrete units. This assumption solved the blackbody radiation problem and revealed that the microscopic world operates according to rules very different from those of everyday experience. Although Planck himself did not fully embrace the radical implications of his work, his discovery laid the foundation for an entirely new branch of physics. It marked the beginning of a journey that would reshape our understanding of matter, energy, and reality itself, setting the stage for all the quantum ideas that followed. The birth of quantum theory did not end with Max Planck's discovery. Instead, it marked the beginning of a profound transformation in scientific thinking. Once the idea of energy quanta was introduced, it began to influence how physicists approached other unsolved problems. At first, many scientists were skeptical. The notion that energy could be emitted or absorbed only in fixed amounts seemed to contradict everything known about waves, heat, and light. Yet, as more experiments confirmed predictions based on quantization, resistance slowly gave way to acceptance. One of the most important developments following Planck's work was the realization that quantization was not limited to radiation alone. Classical physics assumed that matter and energy were continuous, but new experiments hinted that atoms themselves might obey discrete rules. This was a dramatic shift. Atoms were once thought of as tiny versions of everyday objects, obeying the same laws of motion. Quantum theory suggested something entirely different, that the atomic world followed its own unique logic. Planck's discovery also highlighted a deeper issue within classical physics. The failure to explain blackbody radiation was not an isolated problem. Other puzzles, such as the stability of atoms and the specific colors emitted by heated gases, pointed to the same conclusion. Classical theories predicted that atoms should collapse or radiate energy continuously, yet real atoms were stable and emitted light at precise frequencies. These inconsistencies made it increasingly clear that a new theoretical framework was needed. An essential feature of the birth of quantum theory was the changing role of mathematical assumptions in physics. Before Planck, mathematical continuity was almost taken for granted. Physical quantities were assumed to change smoothly without jumps. By introducing discrete energy levels, Planck broke this tradition. His work showed that mathematical convenience alone was not enough. Mathematical structures had to reflect physical reality, even if they appeared strange or counterintuitive. Another crucial aspect of this keynote is the way Planck's idea altered the concept of energy itself. Energy was no longer seen as an endlessly divisible quantity. Instead, it became something with a smallest possible unit, at least in certain interactions. This idea challenged centuries of thinking rooted in classical mechanics. It suggested that nature, at its most fundamental level, might be built from indivisible elements, much like matter was once thought to be made of atoms. The scientific community's reaction to Planck's proposal reveals much about how knowledge advances. Many leading physicists initially rejected or ignored the idea of quantization. Even Planck himself hesitated to interpret it as a true description of nature. Acceptance came not through belief, but through evidence. As experiments continued to support quantum predictions, resistance weakened. This gradual acceptance demonstrates that scientific revolutions are often slow and uncertain, shaped by debate, doubt, and verification. The birth of quantum theory also changed how scientists viewed the relationship between theory and observation. Classical physics often began with intuitive principles and then tested them experimentally. Quantum theory reversed this process. Strange experimental results came first, forcing theorists to construct models that matched reality, even if those models defied intuition. This shift emphasized that human intuition, shaped by the macroscopic world, is not always a reliable guide at microscopic scales. Another major consequence of Planck's work was the introduction of probability into fundamental physics. Although Planck himself did not fully develop this idea, quantization hinted that certainty and determinism might not apply universally. If energy exchanges occurred in discrete jumps, then predicting the exact behavior of individual particles could become inherently uncertain. This planted the seeds for a new understanding of physical laws, one based not on certainty, but on statistical likelihood. The philosophical impact of the birth of quantum theory cannot be ignored. Classical physics supported a deterministic world, where the future could, in principle, be predicted exactly if all initial conditions were known. Quantum theory began to challenge this belief. It suggested that randomness might be built into the fabric of reality itself. This idea raised profound questions about causality, free will, and the limits of human knowledge. The importance of Planck's constant further illustrates the depth of this transformation. This tiny number defines the boundary between the classical and quantum worlds. When physical actions involve values much larger than Planck's constant, classical physics works extremely well. When they approach its scale, quantum effects dominate. This insight explained why the everyday world appears predictable and continuous, while the microscopic world behaves in strange and unfamiliar ways. The birth of quantum theory also reshaped scientific education and research. New mathematical tools and concepts were required to understand quantized systems. Physicists had to rethink long established ideas about motion, energy, and measurement. Universities and research institutions gradually adapted, training a new generation of scientists capable of working within this emerging framework. This intellectual shift laid the groundwork for rapid progress in the early 20th century. Beyond physics, the implications of quantum theory eventually extended into chemistry, materials science, and technology. Although these applications were not immediately obvious at the time of Planck's discovery, they all trace their origins back to the idea of quantization. The understanding of atomic structure, chemical bonding, and electrical behavior all depend on quantum principles. Thus, the birth of quantum theory was not just a theoretical milestone, but the foundation of much of modern science and technology. Another key lesson from this first keynote is the role of creativity and courage in scientific discovery. Planck did not set out to change the world, but he was willing to make an unconventional assumption when conventional methods failed. This willingness to question deeply held beliefs, even reluctantly, is often what drives major advances. His work shows that progress sometimes requires stepping beyond comfort zones and accepting ideas that initially seem absurd. The transition from classical to quantum thinking also demonstrates the importance of limits in scientific theories. Classical physics remains incredibly powerful and accurate within its domain. Quantum theory did not replace it entirely, but rather extended our understanding into realms where classical ideas no longer apply. This layered view of knowledge emphasizes that no theory is absolute. Each has a range of validity defined by nature itself. As the implications of quantization became clearer, it inspired other scientists to explore its meaning more deeply. The idea that energy levels are discrete encouraged further investigation into atomic structure and radiation. This momentum would soon lead to new models of the atom and a more complete formulation of quantum mechanics. Without Planck's initial step, these later breakthroughs would not have been possible. In conclusion, the birth of quantum theory represents far more than the solution to a single scientific problem. It marks the moment when physics began to move beyond classical certainty into a new realm of discrete values, probabilities, and fundamental limits. Max Planck's introduction of energy quanta challenged long-standing assumptions and revealed that the microscopic world operates according to principles unlike anything observed at human scales. This first step in the quantum journey transformed not only physics, but our entire understanding of nature. It laid the foundation for future discoveries and set humanity on a path toward one of the most successful and intriguing theories ever developed, a theory that continues to shape science, philosophy, and technology to this day. The failure of classical physics at the atomic scale represents one of the most important realizations in the history of science. For more than 2 centuries, classical physics had been extraordinarily successful. The laws developed by scientists such as Newton, Maxwell, and Boltzmann explained motion, heat, electricity, magnetism, and light with impressive accuracy. These laws worked so well in everyday life that physicists believed they were universal. By the late 19th century, there was a widespread feeling that physics was almost complete, and that only small details remained to be refined. Yet this confidence would soon collapse when scientists began to investigate nature at extremely small scales. Classical physics is based on several key assumptions. One of the most important is continuity. According to classical ideas, physical quantities such as energy, position, and momentum can change smoothly and take any value. Another assumption is determinism. If the initial conditions of a system are known precisely, then its future behavior can be predicted exactly. These ideas matched human intuition and everyday experience. A thrown ball follows a smooth path, heat flows gradually, and waves spread continuously through space. However, when scientists tried to apply these same principles to atoms and radiation, they encountered serious contradictions. One of the earliest signs of failure appeared in the study of atomic stability. According to classical electromagnetism, electrons moving around a nucleus should continuously emit electromagnetic radiation. As they radiate energy, they should lose speed and spiral inward, eventually collapsing into the nucleus. This process should happen extremely quickly, in a fraction of a second. If classical physics were correct, atoms could not exist in a stable form. Yet atoms are clearly stable, and matter does not collapse. This contradiction showed that classical theory was fundamentally incompatible with the structure of atoms. Another major failure of classical physics appeared in the explanation of atomic spectra. When gases are heated or electrically excited, they emit light at very specific colors, forming sharp lines rather than a continuous spectrum. Classical theory predicted that atoms should emit radiation across a wide range of frequencies, depending on their motion and energy. It could not explain why only certain precise wavelengths appeared. These spectral lines were consistent and reproducible, indicating an underlying order that classical physics failed to describe. The problem of blackbody radiation provided even stronger evidence that classical physics was incomplete. Classical theory predicted that as the wavelength of radiation decreased, the energy emitted by a hot object should increase without limit. This led to the ultraviolet catastrophe, an absurd prediction that contradicted experimental results. Measurements showed that radiation intensity rises to a peak and then falls at shorter wavelengths. The inability of classical physics to explain this behavior revealed that something was fundamentally wrong with the assumption of continuous energy exchange. Another important area where classical physics failed was the photoelectric effect. When light shines on a metal surface, electrons are ejected from the metal, but only if the light has a frequency above a certain threshold. Classical wave theory predicted that the energy of light depends on its intensity, not its frequency. According to classical ideas, even low-frequency light should eventually eject electrons if the intensity is high enough. Experiments showed the opposite. Increasing intensity did not help if the frequency was too low. This behavior could not be explained by classical physics and directly challenged the wave-only view of light. Heat capacity also posed a serious problem for classical theory. Classical physics predicted that atoms in a solid should store energy in a simple, uniform way. According to these predictions, the heat capacity of solids should remain constant as temperature changes. Experiments showed that this was not true. At low temperatures, heat capacity drops dramatically, deviating from classical expectations. This mismatch indicated that atomic motion and energy storage did not follow classical rules. The failure of classical physics at the atomic scale was not due to poor experiments or minor errors. The experimental data were precise, consistent, and reproducible. The problem lay in the theoretical framework itself. Classical physics had been developed based on observations of large-scale systems where quantum effects are negligible. When scientists attempted to extend these ideas into the microscopic world, they assumed the same rules applied. Nature proved otherwise. One reason classical physics failed is that it relied heavily on human intuition shaped by everyday experiences. Humans do not directly perceive atoms, electrons, or photons. Our senses evolved to interpret the macroscopic world, where quantum effects average out and become invisible. As a result, classical concepts such as smooth motion and definite trajectories feel natural to us. At the atomic scale, however, these concepts no longer apply in the same way. Another limitation of classical physics was its treatment of measurement. In classical theory, measurement is passive. Observing a system does not change its behavior. At the atomic scale, this assumption breaks down. Measuring extremely small systems often involves interactions that significantly disturb them. Classical physics had no framework to account for this effect, leading to incorrect predictions and interpretations. The idea of infinite divisibility also contributed to classical failure. Classical physics assumes that physical quantities can be divided endlessly into smaller parts. At the atomic scale, experiments showed evidence of minimum units, such as discrete energy levels and fixed charges. These findings directly contradicted the classical assumption of continuity and suggested that nature has built-in limits. As these failures accumulated, physicists began to realize that classical physics was not universally valid. This realization was deeply unsettling. Classical laws were elegant, mathematically powerful, and incredibly successful in their domain. Accepting their limitations required a major shift in mindset. It meant acknowledging that even the most trusted theories could fail under certain conditions. Importantly, the failure of classical physics did not mean it was wrong. Classical physics remains extremely accurate for large objects and everyday phenomena. Its failure was one of scope, not correctness. It simply could not describe phenomena at very small scales, where new rules apply. This distinction became a crucial insight in the development of modern physics. The recognition of classical failure also changed how scientists approached theory building. Instead of assuming that existing laws were universal, physicists became more cautious. They began to test theories across different scales and conditions. This shift encouraged openness to radical ideas and prepared the scientific community for the acceptance of quantum theory. Another significant consequence of this failure was the breakdown of strict determinism. Classical physics suggested that the future is fully determined by the past. At the atomic scale, experiments hinted that outcomes could only be predicted probabilistically. This challenged deeply held philosophical beliefs about causality and predictability, forcing scientists to rethink the nature of physical law. The failure of classical physics at the atomic scale also highlighted the importance of experimental evidence over philosophical preference. Many physicists were reluctant to abandon classical ideas because they were intuitive and aesthetically pleasing. However, nature did not conform to these preferences. The growing mismatch between theory and experiment made it impossible to ignore the need for a new framework. This period of crisis in physics was not a sign of weakness, but of strength. It demonstrated the self-correcting nature of science. When evidence contradicts theory, the theory must change. The willingness to accept failure and search for better explanations is what allowed physics to progress beyond classical limitations. In summary, classical physics failed at the atomic scale because its core assumptions, continuity, determinism, passive measurement, and infinite divisibility, did not match experimental reality. Phenomena such as atomic stability, discrete spectra, blackbody radiation, the photoelectric effect, and heat capacity could not be explained using classical laws. These failures revealed that the microscopic world operates according to principles very different from those governing everyday experience. Recognizing this failure was a crucial step in the quantum journey, as it created the intellectual space needed for a new theory of nature to emerge. The growing awareness of classical physics failing at the atomic scale created a deep intellectual crisis among physicists at the turn of the 20th century. What made this crisis especially troubling was that classical physics did not fail gradually. Instead, it failed in clear, undeniable ways when confronted with precise experimental results. These failures could not be fixed by small adjustments or corrections. They pointed to a fundamental mismatch between classical ideas and the true behavior of nature at microscopic levels. One of the most disturbing implications of classical failure was the breakdown of the idea of definite trajectories. In classical mechanics, particles always have well-defined positions and velocities at every moment in time. This assumption works perfectly for planets, cars, and projectiles. However, experiments involving electrons and atoms suggested that such clear, cut paths might not exist at very small scales. Classical physics had no way to describe systems where motion itself seemed uncertain or discontinuous. The failure also exposed weaknesses in the classical concept of waves. Light, long understood as a wave phenomenon, showed particle-like behavior in several experiments. Classical wave theory could not explain why light sometimes behaved as if it were made of individual packets of energy. This contradiction was not merely technical. It challenged the very categories physicists used to describe nature. The classical distinction between particles and waves began to blur, signaling the need for an entirely new conceptual framework. Another crucial issue was energy exchange. Classical physics assumed that energy transfer could occur in any amount, no matter how small. Experiments repeatedly contradicted this assumption. Atoms absorbed and emitted energy only at specific values, and electrons responded to light in quantized ways. These observations made it clear that continuity, one of the pillars of classical theory, did not apply universally. Energy, and possibly other physical quantities, appeared to be restricted by fundamental limits. The failure of classical physics also revealed the importance of scale in determining which laws of nature apply. Classical theories were developed based on macroscopic observations, where enormous numbers of particles interact and average out microscopic irregularities. At the atomic scale, where individual particles dominate behavior, these averages break down. This insight led to a new understanding. Physical laws may depend on the scale at which systems are observed. This realization had profound consequences for scientific realism. Classical physics suggested that the universe exists independently of observation, with properties that can, in principle, be measured without disturbance. Atomics, scale experiments challenged this idea. Measuring small systems often altered their behavior, making it impossible to separate observation from outcome. Classical theory offered no tools to deal with this interaction between observer and system. The collapse of classical explanations also affected how physicists viewed certainty and prediction. In classical mechanics, uncertainty arises from lack of information, not from the laws themselves. At the atomic scale, uncertainty appeared intrinsic. Even with perfect experimental control, outcomes varied in ways classical theory could not account for. This suggested that unpredictability might be a fundamental feature of nature, rather than a temporary limitation of knowledge. Resistance to abandoning classical ideas was strong, and understandably so. Classical physics was elegant, mathematically coherent, and deeply successful. Many scientists hoped that the failures could be resolved by refining existing theories. However, repeated attempts to save classical explanations only led to more contradictions. The persistence of these failures eventually convinced the scientific community that a radical shift was unavoidable. The failure of classical physics also influenced the development of new experimental techniques. As classical explanations fell apart, experiments became more focused on probing atomic behavior directly. Precision measurements of spectra, radiation, and particle interactions provided increasingly detailed evidence that classical laws could not explain. These experiments played a decisive role in shaping the direction of theoretical innovation. Another important consequence was the separation between classical intuition and physical reality. Scientists had to accept that intuition, formed by everyday experience, could be misleading. At the atomic scale, nature does not behave in ways that align with common sense. Accepting this required a new scientific attitude, one that prioritized mathematical consistency and experimental accuracy over intuitive comfort. The failure of classical physics also reshaped the philosophy of science. It demonstrated that scientific theories are not absolute truths, but models with limited domains of validity. This understanding encouraged flexibility and openness to change. Rather than seeking a single, final description of reality, physicists began to accept that different theories might apply under different conditions. Importantly, classical failure paved the way for creativity. Once physicists acknowledged that old rules no longer worked, they were free to explore new ideas without being constrained by traditional assumptions. This intellectual freedom led directly to the development of quantum concepts such as discrete states, probability amplitudes, and non-classical behavior. The crisis also highlighted the importance of collaboration between theory and experiment. Classical physics often allowed theorists to predict phenomena long before they were observed. In the quantum era, theory and experiment advanced together, each guiding the other. This closer relationship accelerated progress and led to rapid breakthroughs in understanding atomic and subatomic systems. Despite its failure at the atomic scale, classical physics retained an essential role. It continued to describe the macroscopic world with remarkable accuracy. This coexistence of classical and quantum theories demonstrated that scientific progress does not always involve replacement, but expansion. New theories build upon old ones, extending their reach rather than erasing them. The recognition of classical failure also influenced future generations of scientists. It taught an enduring lesson. No matter how successful a theory may be, it must always remain open to challenge. This lesson became a defining principle of modern physics and continues to guide scientific inquiry today. In conclusion, the failure of classical physics at the atomic scale was not a setback, but a turning point. It revealed the limits of continuity, determinism, and classical intuition, exposing a deeper and more complex structure of reality. By confronting these failures honestly, physicists created the conditions necessary for the birth of quantum theory. This realization marked a crucial step in the quantum journey, transforming physics from a science of certainty into one that embraces probability, limits, and the profound mystery of microscopic world. Niels Bohr and the quantum model of the atom represent a crucial step in the development of modern physics, because Bohr provided the first successful explanation of how atoms are structured and why they emit light in specific patterns. Before Bohr, scientists knew that atoms existed, but they could not explain how they remained stable or why they produced discrete spectral lines. Classical physics predicted that atoms should collapse and radiate energy continuously, yet experiments clearly showed otherwise. Bohr's model bridged this gap by combining classical ideas with the new quantum concepts introduced by Max Planck and Albert Einstein. At the beginning of the 20th century, the atom was imagined using early models such as J. Thomson's plum pudding model, which pictured electrons embedded in a positively charged sphere. This model could not explain experimental results, especially the scattering of particles observed by Ernest Rutherford. Rutherford's experiments revealed that atoms have a tiny, dense, positively charged nucleus with electrons orbiting around it. While this nuclear model explained scattering results, it created a serious problem. According to classical physics, electrons moving in circular orbits should continuously lose energy by emitting radiation and spiral into the nucleus. Since atoms are stable, this prediction was clearly wrong. Niels Bohr addressed this problem in 1913 by introducing a radical idea inspired by quantum theory. He proposed that electrons do not move freely in any orbit around the nucleus. Instead, they are restricted to certain allowed orbits with fixed energies. As long as an electron remains in one of these allowed orbits, it does not emit energy, even though it is accelerating. This assumption directly contradicted classical electromagnetism, but it successfully explained atomic stability. Bohr's second key idea was that energy is emitted or absorbed only when an electron jumps from one allowed orbit to another. When an electron moves from a higher energy orbit to a lower energy orbit, it releases energy in the form of light. The frequency of this light depends on the difference in energy between the two orbits. This explained why atoms emit light at specific frequencies rather than across a continuous range. Each spectral line corresponds to a specific transition between energy levels. Bohr applied his model most successfully to the hydrogen atom, which consists of a single electron orbiting a single proton. Hydrogen's emission spectrum had been studied extensively and showed a clear pattern of discrete lines. Bohr calculated the allowed energy levels of the hydrogen atom and showed that the predicted spectral lines matched experimental observations almost perfectly. This was a remarkable achievement and provided strong evidence that his quantum model captured something fundamental about atomic structure. A crucial feature of Bohr's model was the quantization of angular momentum. Bohr proposed that the angular momentum of an electron in an allowed orbit could only take specific values. This condition mathematically restricted the possible orbits and led directly to discrete energy levels. Although Bohr did not fully explain why angular momentum should be quantized, this rule worked and produced correct results. It showed that quantization was not limited to energy exchange alone, but also applied to motion within atoms. Bohr's model had profound implications for how scientists understood matter. It suggested that atoms are not miniature solar systems governed entirely by classical mechanics. Instead, They are governed by quantum rules that have no direct analogy in everyday experience. The idea that electrons can occupy only certain states, and that transitions between states occur suddenly rather than gradually, challenged traditional notions of motion and change. Despite its success, Bohr's model was not complete. It worked very well for hydrogen, but failed to accurately describe more complex atoms with multiple electrons. It also could not explain certain details of spectral lines, such as their fine structure or the effects of magnetic fields. Additionally, Bohr's model still relied on classical orbits, which later quantum theory would replace with a more abstract description. Even with these limitations, Bohr's contribution was revolutionary. His model showed that quantum ideas were essential for understanding atomic structure. It provided a clear example of how classical physics breaks down at small scales and how new principles must take its place. Bohr demonstrated that theoretical assumptions, even those that contradict established laws, can be justified if they successfully explain experimental facts. Bohr also played a key role in shaping the interpretation of quantum theory. He emphasized that quantum physics requires new ways of thinking about measurement, observation, and reality. Although these philosophical ideas were developed more fully later, Bohr's atomic model laid the groundwork for them by showing that atomic behavior cannot be understood using classical concepts alone. The quantum model of the atom transformed science far beyond physics. It explained the structure of the periodic table, the behavior of chemical bonds, and the properties of materials. Modern technologies such as semiconductors, lasers, and atomic clocks all rely on principles that trace back to Bohr's insights. His model marked the transition from early quantum ideas to a deeper and more complete quantum mechanics. In conclusion, Niels Bohr's quantum model of the atom was a turning point in the quantum journey. By introducing the idea of discrete energy levels and quantum transitions, Bohr solved the problem of atomic stability and explained the origin of atomic spectra. Although later theories refined and replaced parts of his model, its core ideas remain central to modern science. Bohr showed that to understand the atom, scientists must abandon classical intuition and embrace the strange but accurate rules of the quantum world. Wave-particle duality is one of the most surprising and important ideas in modern physics, because it reveals that matter and light do not behave in ways that match everyday intuition. For centuries, scientists believed that the universe could be neatly divided into two categories: particles and waves. Particles were thought of as small, solid objects with definite positions, while waves were continuous disturbances that spread through space. Classical physics treated these two concepts as completely separate. The discovery of wave-particle duality shattered this clear distinction and forced scientists to rethink the fundamental nature of reality. The first hints of wave-particle duality came from the study of light. In the 17th century, scientists debated whether light was made of particles or waves. Experiments involving reflection, refraction, and interference eventually supported the wave theory of light. By the 19th century, James Clerk Maxwell's equations provided a powerful mathematical description of light as an electromagnetic wave. This success led most physicists to believe that the question was settled, and that light was purely a wave phenomenon. However, experiments at the beginning of the 20th century revealed behavior that waves alone could not explain. One of the most important was the photoelectric effect. When light shines on a metal surface, electrons are ejected from the metal only if the light has a minimum frequency. Increasing the intensity of light does not help if the frequency is too low. This result contradicted classical wave theory, which predicted that energy should depend only on intensity. Albert Einstein explained this effect by proposing that light consists of discrete packets of energy, later called photons. Each photon carries a fixed amount of energy determined by its frequency. This explanation showed that light behaves like a stream of particles in certain situations. At the same time, light continued to show wave-like behavior in experiments such as interference and diffraction. When light passes through narrow slits, it creates patterns of bright and dark regions that can only be explained by wave interference. No classical particle model could account for this behavior. The conclusion was unavoidable. Light exhibits both wave-like and particle-like properties depending on how it is observed. This dual nature was not a matter of incomplete knowledge, but a fundamental feature of light itself. The idea of wave-particle duality became even more striking when it was extended to matter. In 1924, Louis de Broglie proposed that particles such as electrons also have wave-like properties. He suggested that any moving particle is associated with a wave whose wavelength depends on the particle's momentum. At first, this idea seemed absurd. Particles like electrons were thought to be tiny, localized objects, not waves spread out in space. Yet de Broglie's hypothesis soon received strong experimental support. Experiments involving electrons passing through crystals or narrow slits produced interference patterns similar to those observed with light waves. These results confirmed that electrons, which are undeniably particles, also behave like waves under certain conditions. This discovery completely transformed the understanding of matter. It showed that wave-particle duality is not a special property of light, but a universal feature of the microscopic world. The strange nature of matter revealed by wave-particle duality challenges classical ideas about location and motion. In classical physics, a particle always has a well-defined position and follows a precise path. In quantum physics, particles are described by wave functions that represent probabilities rather than exact trajectories. This means that before measurement, a particle does not have a single definite position, but a range of possible locations. The act of measurement plays a crucial role in determining which outcome is observed. One of the most famous demonstrations of wave-particle duality is the double-slit experiment. When particles such as electrons are fired one at a time through two slits, they still produce an interference pattern over time. This suggests that each particle behaves like a wave and passes through both slits simultaneously. Yet, when detectors are placed to observe which slit the particle goes through, the interference pattern disappears and the particle behaves like a classical object. This experiment highlights the deep connection between observation and behavior in the quantum world. Wave-particle duality also reveals that classical categories like wave and particle are not fundamental descriptions of nature. Instead, they are models that apply in certain situations. Quantum objects are neither purely waves nor purely particles. They are quantum entities that exhibit different aspects depending on how they interact with their environment. This realization required scientists to abandon the idea that physical objects must always fit into familiar categories. The strange nature of matter has profound philosophical implications. It challenges the notion of objective reality existing independently of observation. In quantum physics, what can be said about a system depends on how it is measured. This does not mean that reality is subjective, but it does mean that classical ideas about properties existing independently of measurement are not always applicable at the quantum level. Wave-particle duality also has practical consequences. Modern technologies rely heavily on quantum behavior. Electron waves are essential for understanding the structure of atoms and molecules, which in turn explains chemical reactions and material properties. Devices such as electron microscopes, lasers, and semiconductors operate based on principles that arise directly from wave-particle duality. Despite its success, wave-particle duality remains deeply counterintuitive. Humans evolved to understand a world where objects are either solid or spread out, not both at once. Quantum physics shows that the universe at its most fundamental level does not conform to this intuition. Accepting this requires a shift in how we think about reality, causation, and knowledge. In conclusion, wave-particle duality reveals the strange and fascinating nature of matter and light. It shows that the microscopic world cannot be described using classical concepts alone. Light behaves as both a wave and a particle, and matter exhibits the same duality. This discovery forced a complete rethinking of physical theory and laid the foundation for quantum mechanics. By embracing this dual nature, scientists gained a deeper and more accurate understanding of the universe, one that continues to challenge and inspire our understanding of reality. Werner Heisenberg and the uncertainty principle represent one of the most profound shifts in the way humans understand nature. The uncertainty principle does not arise from limitations in experimental technology or human skill. Instead, it reflects a fundamental property of the quantum world. Through this idea, Heisenberg showed that at the smallest scales of reality, nature does not allow complete precision. This discovery challenged classical physics at its core and forced scientists to rethink concepts such as measurement, certainty, and determinism. Werner Heisenberg was a young German physicist working in the 1920s, a period of intense creativity and debate in physics. Scientists were struggling to make sense of atomic behavior, and classical ideas were clearly failing. Heisenberg approached the problem from a new direction. Rather than trying to describe the exact motion of electrons in atoms, he focused on what could actually be observed and measured. This shift in thinking led him to develop a new form of quantum mechanics, often called matrix mechanics, which avoided classical visual pictures and relied instead on measurable quantities. In 1927, Heisenberg formulated what became known as the uncertainty principle. At its heart, the principle states that certain pairs of physical properties cannot both be known with arbitrary precision at the same time. The most famous example involves position and momentum. The more precisely the position of a particle is known, the less precisely its momentum can be known, and vice versa. This is not a statement about experimental error, but about the structure of reality itself. Classical physics assumes that particles have exact positions and velocities at all times, even if we do not know them. According to this view, uncertainty comes from lack of information or imperfect measurement. Heisenberg's principle overturned this assumption. In the quantum world, particles do not possess simultaneously well-defined values of certain properties. Uncertainty is built into nature, not imposed by human ignorance. One way to understand this principle is through the wave-particle duality of matter. In quantum mechanics, particles such as electrons are described by wave functions that spread out in space. A wave that is sharply localized in position must contain many different wavelengths. These different wavelengths correspond to different momenta. As a result, a particle with a well-defined position must have a wide range of possible momenta. Conversely, A particle with a well-defined momentum has a wave function spread out over a large region of space, making its position uncertain. This mathematical relationship lies at the core of the uncertainty principle. Heisenberg originally illustrated the principle using a thought experiment involving a microscope. To observe an electron's position, one must use light. Using light with a very short wavelength allows for high positional accuracy, but such light carries high energy and significantly disturbs the electron's motion. While this example helped convey the idea, the deeper meaning of the uncertainty principle does not depend on disturbance by measurement. Even in principle, without any experimental interference, quantum systems obey uncertainty relationships. The uncertainty principle has far-reaching consequences for atomic structure. It explains why electrons do not collapse into the nucleus. If an electron were confined to an extremely small region near the nucleus, its momentum uncertainty would become very large, leading to high kinetic energy. This energy prevents the electron from being localized too tightly, resulting in stable atomic structures. In this way, uncertainty is not a flaw, but a stabilizing feature of nature. The principle also marked the end of strict determinism in physics. In classical mechanics, knowing the exact state of a system allows its future behavior to be predicted with certainty. Quantum mechanics replaces this certainty with probability. Even with complete knowledge of a system's wave function, only the probabilities of different outcomes can be predicted. Heisenberg's uncertainty principle played a central role in this transformation, showing that unpredictability is fundamental rather than accidental. Philosophically, the uncertainty principle sparked intense debate. Some scientists, including Albert Einstein, were deeply uncomfortable with the idea that nature could be inherently uncertain. Einstein famously argued that God does not play dice, expressing his belief that quantum uncertainty reflected an incomplete theory rather than a true feature of reality. Heisenberg, along with Niels Bohr, defended the view that uncertainty is an essential aspect of the quantum world. This debate shaped the interpretation of quantum mechanics and continues to influence philosophical discussions today. The uncertainty principle also changed the role of measurement in physics. In classical theory, measurement reveals pre-existing properties. In quantum mechanics, measurement plays an active role in determining outcomes. The act of measurement forces a system into a definite state from a range of possibilities. This does not mean that reality depends on human observers, but it does mean that classical ideas about passive observation are no longer valid. Beyond philosophy, the uncertainty principle has practical implications. It sets fundamental limits on how precisely quantities can be controlled or measured, influencing the design of experiments and technologies. Phenomena such as quantum tunneling, the behavior of semiconductors, and the stability of matter all depend on uncertainty relationships. Modern technologies, including electron microscopes and quantum devices, operate within the constraints imposed by Heisenberg's principle. Importantly, the uncertainty principle does not imply that everything is uncertain, or that science is meaningless. Quantum mechanics is extremely precise in its predictions of probabilities and statistical outcomes. The uncertainty principle simply defines what can and cannot be known simultaneously. Within these limits, quantum theory is one of the most accurate scientific frameworks ever developed. In conclusion, Werner Heisenberg's uncertainty principle revealed a deep and surprising truth about the nature of reality. It showed that at the quantum level, certainty and determinism give way to probability and fundamental limits. By challenging classical assumptions about measurement and knowledge, Heisenberg transformed physics and reshaped humanity's understanding of the universe. The uncertainty principle stands as one of the central ideas of quantum mechanics, reminding us that nature is not always as definite and predictable as our everyday experience suggests. The role of observation and probability in quantum mechanics is one of the most distinctive and challenging aspects of modern physics. Unlike classical physics, where objects are assumed to have definite properties at all times, quantum mechanics introduces a new framework in which outcomes are described in terms of probabilities, and observation plays an active role in shaping what is observed. This does not mean that reality is imaginary or subjective, but it does mean that nature at the microscopic level behaves in ways that are fundamentally different from everyday experience. In classical physics, probability is usually a sign of incomplete knowledge. For example, when predicting the outcome of rolling a dice, the uncertainty comes from not knowing the exact forces and conditions involved. In principle, if all details were known precisely, the result could be predicted with certainty. Quantum mechanics breaks from this idea. Even when a system is described as completely as possible, the theory does not predict exact outcomes, only the probabilities of different results. This shift represents a deep change in how physical laws are understood. At the heart of quantum mechanics is the wave function, a mathematical object that contains all the information that can be known about a system. The wave function does not describe a particle's exact position or motion in the classical sense. Instead, it describes a range of possible outcomes and assigns probabilities to them. For example, rather than saying where an electron is, the wave function tells us the likelihood of finding the electron in different locations if a measurement is made. Observation becomes crucial at this point. Before measurement, a quantum system exists in a superposition of possible states. This means that it does not have a single, definite value for certain properties, such as position or energy. When an observation or measurement is made, the system is found in one specific state. The probability of each possible outcome is determined by the wave function. This process is often described as the collapse of the wave function, although the exact meaning of this idea remains a topic of interpretation and debate. The famous double-slit experiment clearly illustrates the role of observation. When particles like electrons pass through two slits without being observed, they produce an interference pattern, a hallmark of wave behavior. This pattern emerges even when particles are sent one at a time, suggesting that each particle behaves like a wave spread across space. However, when a measurement is made to determine which slit the particle passes through, the interference pattern disappears. The particle behaves as if it traveled through one definite path. This result shows that the act of observation changes the behavior of the system. It is important to clarify that observation in quantum mechanics does not require a conscious human observer. Any interaction that extracts information from a system counts as a measurement. Detectors, measuring devices, or interactions with the environment can all play this role. The key idea is that measurement involves an interaction that forces the system into a definite outcome from a range of possibilities. Probability in quantum mechanics is not a temporary feature that will disappear with better instruments. It is built into the theory itself. Even with perfect experimental control and complete knowledge of the wave function, the outcome of an individual measurement cannot be predicted with certainty. Only the probability of each outcome can be calculated. This idea was deeply unsettling to many early physicists, who were accustomed to the deterministic nature of classical laws. This probabilistic nature is closely connected to the uncertainty principle. Certain pairs of physical properties, such as position and momentum, cannot both be precisely known at the same time. As a result, predictions about these properties must involve probability distributions rather than exact values. The uncertainty principle reinforces the idea that quantum mechanics describes limits on what can be known, not just limits on what can be measured. The role of probability also reshaped the goals of physics. In classical theory, the aim was to predict exact future states of a system. In quantum mechanics, the aim is to calculate probability distributions and statistical patterns. While this may seem less satisfying at first, quantum predictions are extraordinarily accurate. Experiments have confirmed quantum probabilities with remarkable precision, making quantum mechanics one of the most successful theories in science. The philosophical implications of observation and probability are profound. Quantum mechanics challenges the idea that physical properties exist independently of measurement. Instead, it suggests that certain properties become defined only when measured. This does not mean that reality depends on human thoughts, but it does mean that the classical picture of an objective world with fully determined properties at all times is incomplete at the quantum level. Different interpretations of quantum mechanics attempt to explain the meaning of observation and probability in different ways. Some emphasize the role of measurement in classical description, while others propose that all possible outcomes exist in some form. Despite these differences, all interpretations agree on the practical rules of quantum mechanics and its probabilistic predictions. The success of the theory does not depend on choosing a single interpretation. Observation and probability also play a practical role in modern technology. Devices such as lasers, transistors, and quantum sensors rely on probabilistic quantum processes. Engineers do not need to know the outcome of individual quantum events. They design systems that work reliably based on predictable statistical behavior. This shows that probability does not weaken the power of science, but instead provides a new and effective way to understand and control nature. Another important lesson from quantum mechanics is the limits of classical intuition. Humans naturally expect the world to behave in definite and predictable ways, because this is how large objects behave. Quantum mechanics teaches that these expectations do not apply universally. At small scales, probability and observation are not signs of ignorance or imperfection, but essential features of reality. In conclusion, the role of observation and probability in quantum mechanics represents a fundamental departure from classical thinking. Quantum systems are described by wave functions that encode probabilities rather than certainties, and observation plays an active role in determining outcomes. This framework replaces deterministic prediction with statistical understanding, without sacrificing accuracy or reliability. By embracing probability and the special role of measurement, quantum mechanics provides a deeper and more realistic description of the microscopic world, revealing a universe that is subtle, interconnected, and profoundly different from everyday experience. Quantum theory reshaped modern science and technology more profoundly than almost any other scientific development in history. What began as an attempt to understand strange experimental results at the atomic level evolved into a powerful framework that transformed physics, chemistry, biology, and engineering. Today, many of the technologies that define modern life are direct consequences of quantum ideas. Quantum theory not only changed what scientists know about nature, but also changed how science is practiced and how technology is designed. In science, quantum theory revolutionized our understanding of matter and energy. Before quantum mechanics, atoms were poorly understood, and their behavior could not be explained using classical laws. Quantum theory revealed that atoms have discrete energy levels, and that electrons occupy specific quantum states rather than moving in classical orbits. This understanding explained atomic stability, spectral lines, and the structure of the periodic table. As a result, chemistry was transformed from a largely descriptive science into one grounded in fundamental physical principles. Quantum mechanics made it possible to understand chemical bonding at a deep level. The way atoms combine to form molecules depends on the quantum behavior of electrons. Concepts such as electron orbitals, bonding and antibonding states, and molecular energy levels all arise from quantum theory. This knowledge explains why some substances react strongly while others remain inert, why materials have specific shapes and strengths, and why biological molecules such as proteins and DNA function as they do. Without quantum theory, modern chemistry and molecular biology would not exist in their current form. In materials science, quantum theory provided the key to understanding the electrical, optical, and mechanical properties of solids. The behavior of electrons in solids determines whether a material is a conductor, insulator, or semiconductor. Classical physics could not explain why some materials conduct electricity while others do not. Quantum mechanics introduced the idea of energy bands, which explains these differences. This insight directly led to the development of semiconductor technology, one of the most important technological revolutions of the 20th century. Semiconductors are the foundation of modern electronics. Devices such as transistors, diodes, and integrated circuits all rely on quantum principles. The ability to control the flow of electrons at the atomic level made it possible to create smaller, faster, and more efficient electronic components. Computers, smartphones, the Internet, and digital communication systems all depend on technologies rooted in quantum theory. Without quantum mechanics, the information age would not be possible. Quantum theory also transformed optics and communication. The quantum understanding of light led to the invention of lasers, which produce highly focused and coherent light. Lasers are used in countless applications, including medical surgery, barcode scanners, fiber optic communication, manufacturing, and scientific research. Fiber optic networks, which carry data across the world at near light speed, rely on quantum principles governing the interaction of light and matter. In medicine, quantum-based technologies have had a major impact. Imaging techniques, such as magnetic resonance imaging (MRI), depend on quantum properties of atomic nuclei and their interaction with magnetic fields. MRI allows doctors to see detailed images of the inside of the human body without invasive procedures. Other medical technologies, including radiation therapy and advanced diagnostic tools, also rely on quantum understanding of particles and energy. Quantum theory reshaped fundamental physics by unifying previously separate areas of study. It led to the development of quantum field theory, which combines quantum mechanics with special relativity and describes the behavior of elementary particles. This framework underlies the Standard Model of particle physics, one of the most successful scientific theories ever created. The Standard Model explains the fundamental forces and particles that make up the universe and has been confirmed by countless experiments. Beyond physics and chemistry, quantum ideas influenced biology in subtle but important ways. Processes such as photosynthesis, enzyme activity, and vision involve quantum effects at the molecular level. While living systems are complex and often dominated by classical behavior, quantum mechanics provides essential insight into how biological molecules interact and function efficiently. This growing field, sometimes called quantum biology, continues to explore how quantum effects contribute to life itself. Quantum theory also reshaped scientific thinking and methodology. It showed that nature cannot always be understood using deterministic laws and simple visual models. Probability, uncertainty, and abstract mathematical descriptions became central to science. This shift encouraged greater emphasis on experimental evidence and mathematical consistency, even when results defy intuition. The success of quantum theory demonstrated that accurate predictions do not require classical certainty, only reliable probabilistic laws. In recent decades, quantum theory has begun to drive a new technological revolution. Quantum computing aims to use quantum states to perform calculations that are impossible for classical computers. Quantum communication promises ultra-secure information transfer based on fundamental physical principles. Quantum sensors offer unprecedented precision in measuring time, gravity, and other physical quantities. While many of these technologies are still developing, they represent the next stage in the quantum impact on society. The influence of quantum theory extends beyond practical applications. It changed humanity's view of reality itself. Concepts such as wave-particle duality, uncertainty, and the role of observation challenged classical ideas about objectivity and predictability. Quantum theory revealed a universe that is subtle, probabilistic, and deeply interconnected. This new world view influenced philosophy, mathematics, and even how people think about knowledge and certainty. In conclusion, quantum theory reshaped modern science and technology by revealing the true nature of matter and energy and providing the tools to manipulate them at the smallest scales. It transformed physics, chemistry, materials science, medicine, and engineering, enabling technologies that define modern life. At the same time, it changed the way science understands reality, replacing classical certainty with quantum probability. More than a century after its birth, quantum theory continues to shape the future, proving that ideas born from curiosity about the atomic world can transform civilization itself.